Okay, so I'm going to be looking at infrared emission in perovskite quantum dots. So first, let's take a brief look at why you would want to study this. This is not worth it. So there's an interest in quantum dots for photovoltaic and light emitting applications. It's growing every day. Many of these applications rest upon the infrared spectrum, communications, imaging. There's other ones, I didn't want to list them. And so essentially, the more stuff we know about them and their properties in this range, the better stuff we can do. So take a look at the system. So we have this particular perovskite quantum dot. This is what it looks like. You can't really distinguish much of anything. So here's a better look. So we have like our lead right here, and our cesium and our bromines and the ligands surrounding it all. So nice. And so the methodology is kind of based off of this idea where the extension of where different bond lengths have different potential energies, and there's two different sets of potential energies, one for the ground state, one for the excited state, and we apply that to the one-dimensional case for one particular bond, a lead bromine bond. Yeah. And so the blue is the excited state, and then the red is the ground state. And we put an electron in the excited state as per that, with the Hamiltonian looking something like that. So Hamiltonian up and down refers to the Hamiltonian of the upper and lower states, which is what you would expect for a quantum oscillator. But H up down and H down up are diagonalized spring constants for the ground state. And these are the non-adiabatic approximations of the coupling between the two states. And this assumes that the transition occurs so quickly that no movement of nuclei occurs during the transition. So, got that right. So, here's just an example of, here's the emission expectation value. It's based off the difference of energies of the levels. So this one. So here's an example of the dynamics that occur. The blue is the excited state, and the red is the ground state. We can see it kind of goes back and forth between the two. This is for one particular momentum. I guess I should have mentioned that I'm changing momentum. That's kind of important. But so yeah, don't need to watch the entire thing. Here's some results. Tables are boring, so let's look at some prettier results. So we have a table. We have our initial momentums and recombination rates. We'll see it's roughly quadratic for this area of initial momentums. And then looking at emissions, like the emission wavelength, it's fairly stable for lower momentums, but as we go to higher momentums, it's a bit more varied. So here's just some dynamics information for initial momentum set at 5 and initial momentum set at 100. So yeah, I guess.
So what are those blue and orange spotting?
Blue is the probability of the electron in the excited state, and orange is in the ground state. kind of oscillates between the two in lower momentums, but in higher momentums, it just kind of spreads out a bit. Yields get a lot more jagged as momentum increases as well. And so, two main conclusions that I drew from this. Infrared emission rates peak at lower temperatures, specifically 5 atomic units of momentum, or 27 Kelvin. And wavelength of emission is fairly consistent at lower temperatures from about 0 to 100 Kelvin and grows more varied as temperature increases. So. Okay, let's end, Ben. Any questions?
So can you go, I think it's back like 3 slides, where you have the graphic of this one. Sorry, here. What is the emission micro, is that meter?
Yes, that's micrometers.
How do you have a negative micrometer?
I was wondering that as well, to be honest. But whenever I searched up like negative emission, all I got was like carbon, like negative carbon emissions, like greenhouse gases and stuff. So, yes. Okay. So.
Can I try to help?
Yeah.
It's really either very bad error or very big discovery, but maybe hypothetically. At some amplitudes, the potential surfaces cross, and they swap the order of excited and ground.
Okay.
And then the sign flips. And if you just want to wrap out mind around it, then you just change from absorption to emission. Just energy goes different direction.
And then for the rates, can you use Marcus theory to get rates?
This was using Marcus theory. I guess I didn't explicitly state that.
Okay.
No?
But we can do it. Okay. He used parameterization similar to Marcus theory.
Okay.
But not the rate based on Marcus theory. More questions to Ben? Okay, let's applaud how brave he is and please give me stage for a second.
That's fine.